Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL online certification course in structural systems in architecture. Today we are in the module 8. The spatial structure is this module, the last module, and this is the third lecture on that, the 8th module. In continuation, this is the 38th lecture, and today we will be discussing the first part of the structural systems of high-rise building. So, in this lecture the following concept will be covered. We will start with the introduction, then we will go to the interior system, the one of the system that is adopted for the high-rise building structural system. Then we will discuss the various types of the interior systems like rigid frame system, the vertical shear wall system, the frame shear interaction system, and finally the outrigger structure. The learning objective of this particular the lecture will be, we will discuss the fundamentals of the high rise building and the structural systems of that, and then we will going to outline the concept of all the interior type of the building system. So high rise building. So high rise building was actually the dream of the human civilization. So just like people want to fly in air, and they invented the aeroplane, something like that. We also want to have the high rise kind of a structure, and we want to live high rise. So if you see the even before almost about 2000 years BC, the pyramid, the Giza pyramid, that was also treated as one of the high rise structure, but that structure was not a habitat structure. It may be a kind of a cenotaphs, or maybe a kind of a tomb for the pharaohs, but that if you consider the system of the structure or the build of that particular type of structure in pyramid, in case Giza pyramid, this is a high rise, and that kind of man-made high rise structure was stay long in the record book till the Eiffel Tower came into the picture in France, Paris. But even the Eiffel Tower is not as, is a habitat one. It's a tower. It's a kind of a symbolic kind of a victory tower kind of a thing. But this is a structure, you can say it is, which is high rise. But people want to live on the top, and in the mid 1800th century, it was maximum 4 to 5 storied building can be built possible. And the reason behind we cannot go up, because there are 3 typical reasons. One is the too many steps to climb and down every day. This is too much. If you want to construct a building of 10 to 12 floors, even 10 12 floors is too much steps to rise. And as you know, the high rise structure, as you go, the machinery thickness in the ground floor, it will be too thick and or too enlarged, that it will go eat up lot of ground space. So that is another problem, another issue. Not only ground floor, if you go high rise like 10 floors with machinery structure, the load bearing structure, even in the 5th floor onwards, the things will be too high. The thickness of the wall will be too high. The last one is the framing could not go so high because of the unstable wing framing, in the sense of the framing of windows and all, because as and when you go high, you need a toughened glass, and you need also some of the typical lock, like casement window doesn't work over there. So you have to have some other alternative of the windows, otherwise it will be so tough, because as in when you go rise up, the wind pressure is also increased drastically. So for that unstable wind, it is not possible to control over that particular window opening of the windows or so. So those are the typical points that create a mankind to stop dreaming towards the high rise or so. But traditionally, if you see the high rise building, it was, there were some inventions. I will go to the next slide to know that or understand that to the typical invention that is possible to make the building high rise. But before that, let us discuss that traditionally function of the building was tall buildings are as a commercial building, and afterwards it was has some kind of different uses also. We have nowadays the residential high rise building, we have the mixed use high rise building, also the hotel towers, and tall building development was involved, and it is actually nowadays we go for different factors, that different factors play a major role. The first one is the economic factor. Yes, land economy is one of the major criteria. If the land price is very high, so people want to go in that build the high rise building, so you can accommodate lot of function in a smaller footprint or the same footprint of the ground. Aesthetics is another issue, or there is technology is another issue. If you have that technology with you, construction technology, then only you can go or construct high rise building. The municipality regulations is also one of the issue that because of the FAR and the setbacks and all is another thing. So, or some areas there is a height cap, so you cannot they restrict the high rise building, the height of the building, so because of some reasons. And among all those factors, the economics or the economy is the one of the prime governing factor in case of the why we choose high rise or not. Now, as I told you, there are two interesting events was happened in the mid of 1800 to 1900 that year. So that century, and then that make us possible to thought that we can really construct high rise building. The first one is the Bismarck process. This process invented by the Henry Bismuth in 1855. This process he was taken patented, and in this process you can manufacture steel from pig iron, and it can be actually industrial production is possible. Initially it was possible, but it was not industrial production, but it is a small amount, but industrial production possible after this invention of the Bismarck process. So steel is available with us then, and industrial through the industrial revolutions and all. And steel, as you understand, is the one of the important material for the high rise building, because concrete or the machinery it's may not be possible to go that up, because you need to have a kind of a material whose density was low and he is having the strength is very high. From that point of view, that strength by density ratio is very high in case of the steel, and that is a wonderful material for the high rise structure. What is the second invention? Second invention is that in very similar days, 1857, Elisha Otis, he actually invented the shoe of the lift elevator. So what he did is that the Otis elevator company began manufacturing passenger elevator. And as we understand in the very first topic or very first slide, that the climbing too much steps is another problem. To construct a high rise building, that was no more a problem after 1857, because passenger lifts are available through this company. And perhaps you know nowadays also this Otis lift are very much popular in the country or anywhere in the globe. The invention of the elevator allows vertical transportation of people and goods without stair, and that is one of the challenge we can overcome in 1857. So then we can think of the high rise building, and the first high rise building or the early sky cap, if you see, that came in Chicago in 1885, maybe just after 30 years after that Bismarck process, and that's Ellis, that company has started up for that the elevator just after 30 years. It is in Chicago, not in New York. People sometimes has mistaken that the New York is the first originated the high-rise building. No, it is in Chicago. Chicago is given the birth of first high-rise building. That building was known as Home Insurance Building. The photograph is here from Chicago Architect information that website. And this particular building was 10-storied, not much, 10-storied, 42-meter high, but that's too much for those days. And but this building is no more. This building was actually destroyed afterwards. But this building was actually came up in the Chicago in 1871, after the 1871 Chicago fire. What is the character of the building? The physical envelope of this construction was traditional, that is load bearing. They go with a load bearing system. They do not move from the load bearing system to the frame structure system. The thick machinery external wall creates for the comfortable indoor environment. Its wall is thick, large windows, and high ceiling was provided, which doesn't provide now in high-rise building. We go for the thin walls and the low-rise kind of the room heights, and that was allowed, that large window and the high ceiling. It's allowed the good amount of daylight penetration, which was is a good building. This home insurance building was a very energy efficient building as such in those days. The maximum financial return over the fixed plot size, that what I have just now told, that economy drives this, the high rise, initiates this development of modern high rise building in North America during the mid 19th century. So then one after one the building come up, and as and when the new building come up, there are different type of technology and those involved, and the structural systems of these things, the high-rise building is also developed a lot. So if you classify the high-rise building system, so there are two major classifications. The one is called the interior system. The interior system is categorized as the interior structure, that the backbone or the strength material, the strength influence or the strength parameter, the members are all enclosed inside the building. It's in a core point of view. So if you take a kind of a plate, a floor plate, you will see that the core area, or maybe it is distributed from the core to the perimeter area. The interior is taken care of your system within that system. And the second one is of course called the exterior system, where it's the major part of the load bearing, major part, not the maximum, major part of the load bearing system was dedicated in the perimeter area. So that is from the distribution of the major the structural influence, whether it is an interior, throughout interior or core interior, or it is dedicated mostly in the exterior. Based on that, the interior and exterior system was classified. So today in this particular lecture, in this 38th lecture, we will stick into the interior system, and the next lecture will go to the exterior system. So if you see the interior system, there are 4 types, major types. There are maybe much more, and there are some kind of overlap from one to other. But if these 4 are the classically, if you see these 4 are the major classification on the interior system. It starts from the rigid frame system, and then there are vertical shear wall or shear truss system. But this system, the second one, vertical shear wall, is a kind of a system which doesn't exist in practicality, but this system definitely gives a kind of a thought, and that translated to the third system as the frame shear interaction system, and also the last one in the outrigger structure system. So in the rigid frame system, what happened is that the frames are considered as a rigid. What is a frame? Frame is a consist of pillars or the columns and the beams. So it is called the moment resisting frame. It is constructed such a way that it is very rigid, and the construction, the joint between the beam and column is so rigid. It is between the horizontal girder and the vertical column, and it take care of the moment, because it will be the tall building will definitely going to generate a huge amount of moment. If you remember, in the fourth week we discussed about the high rise, I mean the portal frames and all, and a very one or two slides probably. But in that we discussed that if you go base and the stories, if it is high, you have lot of uncertainties and the redundancy, and there will be a sway and all these things, functions will be there. And because of that lateral load and also the gravity load, it will give you lot of moment generated in the beams, in the columns, and also the beam column junction. So here we assume or try to construct that particular rigid frame. Such frames resist load primarily through the flexural stiffness, that is due to the bending stiffness also. The size of the columns are mainly controlled by the gravity load, and the progressive column size increases, as you know it is going to increase, and the columns are distributed thoroughly. The size of the girder is controlled by the stiffness of the frame, ensuring the capacity of the acceptability of the lateral sway of the building. So that is the depth of the girder will be too high, because there will be a sway, there will be kind of a shift because of the wind or maybe from the earthquake, the lateral load. So that has to be resisted. That has to be resisted by this girder. That is why the girder become a little bit stiff. The size of the girder determines that how much it will be, how to protect that sway or those kind of the lateral shift. So this is the one of the schematic diagram. So I have placed the plan as that is very regular, and the footprint of, you see it is a very regular footprint of the columns, and there are beam lines, black color. So those column beam are creating a kind of the rigid the beam column grid in the elevations or in the sections. So good resistance against the gravity load has to be taken care of by the columns, and the performance of this particular the load, that is the lateral load, is taken care of by the beam. So I have written over here, it is a good resistance system for the gravity load, but it is very poor in case of the against the lateral load. That is why you cannot go higher. I mean, you cannot go more than 20 to 30 storied. You cannot go more than that. It will be uneconomical. It will be a lot of problem. That the column sizes increases, the depth of the beam is increases, and your center to center dimension of the column is also going to increase. So those are some of the buildings, which is some Lakeshore Drive apartments. It's a apartment building in the Chicago, and there are building like the New York. Some buildings are there. So those two buildings are designed by the master architect Mies van der Rohe. So those 1849, 1858, those days, and those are the rigid frame system. Then let us go to the next one, the vertical shear wall system. The vertical shear wall system is it's kind of a system where the building is conceptualized as a shear truss standing in freestanding over the ground. Okay, so in that particular system, the lateral load resisting supports are there, and that will primarily take care of the lateral load resisting system, that is from the wind load or those kind of lateral load has to be resisted. So its particular system, that the vertical shear is, that is why it is known as the vertical shear truss. Vertical shear truss. Shear is, why shear? Because it is if you see the lateral load comes to a particular the building or particular the height of the building, it's create a kind of a huge shear in the base. It's a cantilever kind of a thing. So and it will going to resist that primarily by the wind load, wind or earthquake generated lateral load. And this particular building system is actually treated as a cantilever fixed at its base, that I have told you. Now, if you see in this particular system, so we considered the core part as a shear wall. So that particular part, either you have to construct by the concrete shear wall or the steel braced frame shear wall. Steel braced frame shear wall will be look like this. If you have to densify these bracings, or sometimes you may go with you increase the suppose the diagonal bracings or something like that. So you have to increase the quantum of the structural member over there, that is the steel braced frame. So that creates this particular core, and this particular core will be taken to from the ground or from the foundation to the top, and that is act as a primarily lateral load resisting frame. So this particular frame, when you have and there are some outward areas, that is this areas is also there, but significantly less amount of structural systems will be there. Okay. So in that vertical cantilever act as a vertical cantilever, and when there is a kind of a force, that wind load or whatever may be there, this is the wind load or whatever, or maybe earthquake load is there, then it's act as a pure cantilever. And as when there will be a shift, and this shift will be determined by how much is the depth or so, what is your depth and what is your height of the building. These two are the very important criteria of your this shift. And definitely this depth is the depth of your core depth, that is your this shear truss depth. And how much is this delta, the shift is determined by this depth and the height ratio. And because of that, if you try to see the shear force diagram, it's very increasing, and in the base it is have to have a very high amount of shear force, right? And this shear has to be taken into account. So that is why you need in the base the shear wall or this particular bracing, which is I have just now shown, that you have to intensify the amount of structural the quantum of the structural material, so that it can resist the shear force. The shear force has to be resisted. That is actually happening in the ground plane. So this is the typical system that I have just now told. It has to be a very rigid kind of the frame has to be there. So you can definitely control over the deflection. The deflection is under control. Under lateral load will be under control. So the next system, which is the frame shear interaction system. So name suggests it is the merging or the amalgamation between the last two systems what we have discussed. The frame we have discussed and the shear core we have discussed. Now if you just put both into that, we will get some kind of advantages. The rigid frame I have write down, the rigid frame is not efficient for a building which is over 30 stories, because of the sway that we have discussed, that because of it is going to sway too much, because lateral resisting things are very weak. Only the beams are there. Columns are actually mainly essentially take care of the gravity load. It's cause a huge amount of bending and this kind of excessive amount of the load and that. So it will going to bend. The outcome of this particular the frame structure is the shear racking of those one after another floats. That going to influence your deflection criteria and the bending of the columns, and it will take the bending of the columns and all the bend, and the girder will sway, and it will give you a huge amount of sway after a certain height. So that is why after 30 storied and all, the amount of sway is so high that you may feel in the if you I mean in the balcony, or maybe if there is a little bit of high wind, you may feel that particular building is moving or kind of I mean it's swinging kind of a thing. but that is not permitted from the serviceabilities or all those kind of issues. To stop that one, to make the building that stop that one, you have to make more rigid frames, or that sometimes uneconomical. So, and this is another type, that is vertical shear truss, that I have also told you, that is rigid, that controls sway because of the depth and the height criteria, and it's actually act as a shear wall. So, the vertical shear truss I have written like it's alone can provide the resistance up to 35 story, because that has another problem, that cannot have a larger influence area. Larger influence area is not possible, so it can be core into that, so that can go up to the 35th floor or so, and that is going to have the cantilever effect that I told you. Now, if I merge these two together, how to merge? The rigid frame and the shear truss can be merged like this. So, the shear truss is in the core, and that will take care of the main the function of the lateral movement, and the frame will take care of the gravity movement. Then you can go little bit more higher, maybe another 10 to 15 floor more you can add up without any problem. So, this lower part of the, in case of the lower part, the frame is restrained by the truss, right. But in the upper part, what happened? The truss is restrained by the frame. So, that means as there is a sway problem in the top part, the truss is there, that will be restrained your that will make a control over your sway. And in the ground part, because your footprint is less, so your gravity load has to be actually fall. I mean, you have to actually transmit that to the ground. So, in that case, you need somebody to do that. So, that in that case, the frame will restrain the truss. So, that is the beauty of this particular system. So, finally, the effective process in that cases, we can have a lateral rigidity of the building along with the vertical or the gravity load transmissions. So, this is one of the again a skeleton figure. So, you have a core inbuilt inside the frame system. Frame is there. So, they are taking little larger area, larger influence floor plate area, an internal core, and there are some kind of a resisting frame. The outside it is the gravity load resisting case, and the central area can be taken up of the lateral resisting kind of a load. So, this is lateral, and this is again the gravity. So, it is something like you can say the human skeleton, if you see, and if you see like we have a spinal cord. So, that is the rigid that is the shear core, and we have the also this particular the ribs and all, which are the frames. So, you can think of something like that, how the God is also created our human body as a this frame and shear truss kind of a combinations. So, those are the some buildings which are the example of Empire State Building, and in this Chicago building is the example of that. The third system, or this fourth system, is called the outrigger system. In the outrigger system is also the further development of the frame system, frame shear interaction system. It has a central core as it is. It has the frames also as it is. It has a perimeter column. See, this is a perimeter column in the perimeter of the building, and it has a outrigger. What is outrigger? Outriggers are generally in form of the horizontal trusses. So, those are the horizontal trusses, outriggers, the blue color one, and in steel, or in case of the concrete, it is a deep beam. So, this outriggers serve as to reduce the overturning kind of effect, and this will going to give you further benefit from the bending moment point of view when it is you can imagine that as the vertical cantilever. So, let us go to the next slide. So, this is the typical cross sections of the outriggered structure. After such and such interval, so you can give some kind of a belt kind of a the floor, which will have a intensified diagonal trusses and all, or maybe the shear wall. So, that flank into till the perimeter column, and that floor maybe you can think of that is the service floor of your tall building, because tall building required some kind of service floor at the interval of 10 to 12 floors. So those can be used, the service floor can be used as a belt truss floor or the intermediate floor. There will be a bottom belt truss and the top belt truss also. So here what is going to happen after the load transfer, if you do not have any kind of a outriggered this bracing, which is the belt truss, your bending moment of this thing is generated like. So this is a case of a the high rise building. You imagine that is as a cantilever thing, it is like this, right? So let me erase this. But if you do this the outrigger, so in all these outriggered point the bending moment is reduction, there is a reduction in the bending moment. So there is, this is the outriggered point, so there is a reduction in the, so finally at the it is absorbed, this belt will going to absorb as a stiffener, it will going to absorb because of its material property, it will going to absorb some amount of bending moment. And due to that there are in the ground plane there are a considerable amount of less amount of bending moment will be there. There is another benefit in this outrigger structure, if you have a lateral load, so this will it will bend like this. So one portion of the column will be under tension and another portion column, leeward side column will be under tension. So this particular connectivity will give you kind of stabilize the thing, and that will be actually acting overturning effect, that will be counteracting the overturning effect, that I have told you that outrigger are counteracting the overturning effect. So its couple has to be taken care of and neutralize the thing by the deep this kind of the belt truss. So outrigger structure is always going to be compare, if you want to compare with a sailing boat. So the exterior columns are those stays, so these are some of the stays you see. So those are the exterior column or perimeter column, whatever I told you, and this the central post or the mast is your core, and those are your outriggers. So see, this is because of this particular the structure in the sailing boat structure, the sailing boat is actually going to be stable under the force of wind. It's take care of your any kind of the overturning moment. In fact, if there is a kind of a problem in the water or this in the sea because of the wave, or also from the the wind generated thing. So those are the two very interesting or important building in the history of the our the tall building, the Jiomao Tower building, which is in Shanghai, and also the Taipei 101 in Taiwan, are under based on this particular outrigger. So those are the references, and this is the conclusion that the interior structure is having some kind of the high rise building is classified into two way, interior and the exterior, and the interior system mainly because of the rigid frames and the shear core. Thank you very much.